You must have seen this formula to find the sum of an arithmetic series. Have you ever wondered why it's true, or how did this formula appear? In this video, we will uncover the fascinating story behind the formula and explore the world of arithmetic series. But before we get into the formula, let's understand what an arithmetic series is. An arithmetic series starts with a constant value a. Then each term is derived by adding a constant term d to the previous term. The general formula to find the nth term of arithmetic series is a plus n minus 1 times d, where n represents the number of terms and d is the common difference. Common examples of arithmetic series include the natural, odd, and even numbers. However, the most intriguing aspect of an arithmetic series is its sum. Let's start with a simple example, the sum of first 100 natural numbers. Imagine if there were no formula discovered. How would you do it? Feel free to pause and ponder. Well, a German mathematician named Carl Friedrich Gauss came up with a brilliant method to find the sum at a very young age. He observed that the terms at the same distance from the first and last term add up to the same value. For example, the first and last terms, the second and second to last terms, and so on, all sum up to 101. Since the order of addition doesn't matter, we can cleverly reorder the numbers by adding the first number with the last number, the second with the second last, and so on. We find that this pair adds up to 101. With 50 pairs in total, the sum of the first 100 natural numbers is 50 times 101, which equals 5050. Now, let's move on to reducing the formula for the sum of first n natural numbers. Instead of pairing the numbers as we did before, we can assume the sum to be s and line up the sum in two rows. In the first row, the numbers go up, and in the second row, they go reverse. Summing up, we observe that each column adds up to n plus 1. The total sum of both rows is twice s, which equals the number of terms multiplied by the sum of each column. Therefore, the required sum s is the half of total sum. We have deduced the formula algebraically, but let's explore a more visual and intuitive way to understand this sum. We can represent the sum of numbers as a series of dots arranged in a triangular fashion. By taking a copy of this triangle, inverting and joining it with the first one, we notice that the dots form a rectangular shape with dimensions n by n plus 1. The total number of dots in this shape is equal to n times n plus 1. Hence, the sum s is the half of total number of dots, which equals n times n plus 1 over 2. Now that we know how to calculate the sum of natural numbers, let's extend our formula to any arithmetic series. Suppose sum of the series is denoted as s. We can reorder this by bringing all a's and terms containing d together. Factoring out the d, we can simplify it. The first part of the sum is straightforward, n terms multiplied by a. For the second part, we use our formula for the sum of first n natural numbers, replacing n with n minus 1, since we have n minus 1 terms here. After further simplification and factoring out n by 2, we obtain the expression for the required sum. In case if you are wondering about another proof, here is one for you. For any arithmetic series, terms at the same distance from the first and last term add up to the same value. Using this property, we can deduce the expression for the sum just like we did for the natural numbers. By writing the sum in two rows and adding up each column, we find that it adds up to twice a plus n minus 1 times d. Simplifying further, we obtain twice the sum of each row equals n times the sum of each column. The required sum s is the half of the total sum. Now let's test if this formula holds true for the natural numbers. If we replace both a and d with 1 in our formula, we get the expression that exactly matches the sum of the natural numbers.